Good morning, friends. Here we are. We're in chapter 11, looking at section 4. We're going to discuss areas of regular polygons and composite figures. If we look, we've got a little bit of vocabulary here, and I started breaking it down for myself. The center of a regular polygon. Here's a regular polygon. You remember what it is. All the sides are congruent. All the angles are congruent. So in this case, we're going to pretend this is regular hexagon. This is the center. The center is exactly what you think it would be. It would be the center, right? If you were to circumscribe a circle around it, it will be the same center of the circle as the center of that regular polygon. The radius of the regular polygon will be from the center, the segment that connects the center to any one of the vertices. So that's how you're going to determine what the radius is. Now we have this idea of an apothem. The apothem, I'm going to need both sides, both of these radii to talk about it. The apothem is going to be referring to the distance from the center to the very edge, but we're talking about like the perpendicular distance. So I'm talking about this line right here. It's going to be the apothem. In a way, we can call it the height of the triangle at that particular point. The central angle of a regular polygon, if you take two consecutive vertices, and then you have, or two consecutive radiuses, lines to the vertices, and you have, let's say, some angle x, you can't see that, neither can I. Let's say x is a limey green color. Then what you want to do is recognize that that's the central angle of your regular polygon. So that's going to be the angle. And composite figures. So when you have composite figures, basically, I think you've seen them before. It would be kind of finding the area of a shaded region kind of thing, or finding the area of two figures together. So let's say I have this shape, which we all know to be a square, and then let's say I have a semicircle on the side. I might ask you to find the area of this whole thing, which would be a composite figure. And you'll see other versions that are better drawn and more better articulated, and that might actually deal with a regular polygon a little bit better. So that's our vocabulary. Let's get on to some examples. This is just another picture of what we were talking about. I thought I'd use it. Probably should have because it's prettier, but that's okay. All right, let's get to our first example. So here we are. We've got FGHJ, and it's inscribed in circle K. Identify the center of the radius, an apothem, a central angle of the polygon, and then find the measure of the central angle. Okay, I think we can handle this. So the first thing we need to do is identify the center, and the center is at K. Not surprising, and I'll just use a pen to kind of do that. All right, so there's identify the center, the radius. I'm going to trace in dark blue. And we've just been through this, so I know you guys are like, this is too easy. The apothem, I'll let that be purple. That's my apothem. And a central angle of the polygon, then find the measure of the central angle. So the central angle is going to be this angle here, right? So it's going to be, let's use a different color again. So it's going to be this angle here. It's going to be the measure of the angle between two consecutive radii. So with that in mind, what is this angle? Well, we know that it is, we think about this as 360 degrees. We know that we're going to fit 4 triangles like that right in this circle, right in this center here. And so if we take 360 and divide it by 4, you guys know we get 90. And so the measure of the central angle would be 90 degrees. Okay, so next we have art by Kang. Kang created this stained glass window shown. The window is a regular octagon with a side length of 15 inches and an apothem of 18.1 inches. What's the area covered by the window? So if you look at the situation here, the apothem is the height of that one triangle. The what else did they give us? And an apothem of 18 inches. And what is this? The base is 15. Well, I think you guys see what's happening. If we find the area of this triangle and we know that there are 1, 2, 3, 4, 5, 6, 7, 8 of them, we're going to find the area of the triangle multiplied by 8. So the area of a triangle is 1/2 base times height. The base in this case is going to be 15. The height is 18.1. And then I know that I'm going to multiply my answer ultimately by 8 because I need to do 8 times the area of the triangle. So I'm going to have to multiply my answer by 8. And that really becomes 4. So we get 4 times 15 times 18.1. And with the magic of calculators, voila, we have 1,086 inches squared. Make sense? So we just did that. And so this is kind of alluding to a formula here. To find the area of a regular polygon, what we're going to do is, we know that we're going to have to, whatever the number of sides is, let's say to find the area of an n-gon, right? An n-sided figure, and we know we're talking about a regular polygon here. So to find the area of an n-gon, what we're going to do is take that n-gon, the number of n sides, and we're going to multiply it by the area of the triangle, 1/2 the base, or maybe the side, times the apothem. And so n times 1/2 times the side times the apothem, that's the area of a regular polygon. And then what I can do is simplify that by saying that that's going to be the side times the apothem times the number of sides over 2. I don't know how the textbook wrote it down, but I'm going to write it like this. I don't like using the capital A either. So I'm going to do this. 1/2 of n times the side times the apothem. Boom. That's our area. And we definitely need that information for this problem. So here's what we got. We're looking at a regular hexagon, and the regular hexagon has a side length of 3. I'm going to try to draw it, but I mean, do I have to? Okay, I'll draw it. So if I draw the hexagon as best I can, I know that I'm dealing with these 6 triangles, right? And these 6 triangles would have the area of 1/2 base times height, and then I'm going to multiply that by 6. So basically, we're using that formula we just talked about. So 1/2 of the number of sides, 3, times the base times the height. But in this case, the base is going to be the side length, and the height is going to be the apothem. So 3 times S times A is going to be my answer. They gave us the side length of 3, which is totally cool. So we've got 3 times the apothem, but we don't have the apothem. And so we're going to have to take this triangle that's here, and that's like me projecting. No. Okay, so I'm projecting it over here. I recognize that this side is 3. This particular type of polygon, this hexagon, has a 60-degree angle here, and then these 2 angles are congruent. I'm going to figure out that these are 60-degree as well. So I know that each of the sides are 3. And even more interesting is that when I drop the apothem, I'm creating 2 30, 60, 90 right triangles. Since these are 30, 60, 90 right triangles, we know a lot about finding the length of the sides. We know that this side opposite the 30-degree angle, I'm just talking about this little bit here, is going to be 1.5, 1/2 of 3. We expect that the side opposite the right angle is double that, which is 3, 1.5 times 1.5, which is 3, and then 1.5 plus 1.5, which is 3. And we know that this bad boy across from the 60 degrees, the height, or the apothem, is equal to 1.5 times the square root of 3. Remember, it's equal to the small side times root 3, or S root 3. And so now I'm going to take that information and plug it in. Just because I'm enjoying life right now, I'm going to change this to 3 over 2. It's just my preference. And because that's the same as 1/2, and I'm going to multiply it all together, I get 27 over 2 times the square root of 3 as the area. And they asked me to round it to the nearest tenth. So with the magic of calculator, I get 23.4 meters squared. All right, so let's look at this same situation, but we're talking about a regular pentagon. The area of any regular polygon is going to be 1/2 of the number of sides times the side times the apothem. And so now I'm not even going to draw the picture. I'm going to see if I can do it without. We're given that the radius is 10, and so that means I'm going to have to draw the picture. One of the 5 triangles has the side length of 10, and then we have to figure out the rest of the information in here. Let's see, to figure out the apothem. All right, how can I find that? What can I do? I should probably find some information about the angles. I know that this top angle was going to be 1/5 of 360 degrees, right? Because if we think about 5 triangles coming together to make 360 degrees, that intersection in the center, those central angles, when I do that, I take 360 and I divide it by 5. And when I do that, I get, let's say, 72. So this angle up here, this large one, is 72. If the large angle is 72, when I cut 72 in half, I get 36. So this is a 36-degree angle, and this is a 36-degree angle. Still no apothem, but I'm at least getting more of this triangle figured out. The next thing I'm going to do is figure out the other angles. If this is 90, because this is a perpendicular line, then I know that I can find these two base angles. It's going to be 90 minus 36, basically. It has to be a complement. Let me make this larger. I'm looking at it funny, and I'm thinking, boy, these kids can't see it. So, better? Thank you, babies. You should have just said it before. All right, so now we need to figure out this base angle, and we recognize that it has to be a complement to 36. So 90 minus 36 is like 90 minus 40, which is 50, but add some more, it's going to be 54. So both of these angles are 54 degrees. Let's just hold there for a second. We still don't know anything about the apothem, but you know what? Back in the day, like chapter 7, 8, I don't remember what it was, we talked about finding information about the sides of a triangle when we know it's a right angle triangle. You guys remember, I'm talking trigonometry, right? So what I can do is rock some SOHCAHTOA back in the day. So I'm standing here at this angle, and I want to know this side. So I'm going to use what I got to get what I want. I've got that this is 54 degrees. I've got the hypotenuse. I want the opposite. Which one of my trigonometric ratios requires opposite and hypotenuse? SOHCAHTOA. Hopefully you thought sine, and if you did, you're correct. So the sine of 54 degrees has to be equal to this thing that I'm looking for, the apothem, over 10. The hypotenuse. And so now I'm going to do the work. Again, the magic of calculator will get me the answer, but here, let me set myself up because I don't want to waste time. I have 10 times the sine of 54 degrees. It has to equal A. Remember, if you're using your calculator, you need to make sure you're in degree mode. So I end up with 8.1 as my, what are we dealing with, inches, as my apothem. Still not done, but we're pretty much almost done. So now that I've found my apothem, the next thing I'm going to do is look for the area. The area has to be the number of sides, which is 5 over 2, times the side length. And this side length, remember, we never found the sound length. Hun, hun, ha. That's okay. The side length we're going to find by using maybe Pythagorean theorem. I don't know. Let's do it. I don't know. I guess I could use like cosine, but I'm going to do Pythagorean theorem because I'm living that kind of life right now. So 8.1 is this length, quantity squared, plus this base squared, this little base squared, is equal to 100. 8.1 squared gives me 65.61, and then when I do a little bit of math magic, b squared has to equal 100 minus 65.61, and that gives me like a 34.35 or something like that, and we get from there, when I take the square root, that the base is equal to, glancing at my calculator, 5.86, 5.9. So the base is 5.9. And if the base is 5.9, I've got to double it. Gosh, this is the problem that keeps on giving. I've got to double 5.9. And when I do that, I get 11.8. Yeah. So then now, finally, 5 over 2 times the side length, the whole side of the triangle has to be 11.8 times the apothem, which we got as approximately, let me put that in parentheses so it don't look crazy, 8.1. And again, one last time, I dance with my calculator. I end up with 239.0 inches squared of pentagon awesomeness. All right, we have this one. Here's a composite function. We got like a little circle, half circle here, rectangle, and a triangle. And I think I don't really have a whole lot of time to do this. Can you do it? How about this for a change of pace? If you do this and you send me it in a picture, I will give you extra credit if it's right. I know the answer's in the book, but just show me work. All right, guys, I'll see you soon. I think you can do this problem for real, but if not, let me know. I hope. Take care. Bye-bye.